One of the very best analogies to help people understand how hypothesis tests work is to liken it to a criminal trial. Two hypotheses are basically placed before a jury, and you have to assume innocent until proven guilty, right? Same here. So a key point is that the null hypothesis always gets the benefit of the doubt and is assumed to be true throughout the entire testing procedure. Only at the last step can you decide that the observed outcome is extremely unusual under the assumption that the original null hypothesis is true. And then and only then do you reject the null hypothesis. So only two outcomes are possible in a hypothesis test. The first one is that we do not find any evidence to support the alternate claim. Nothing was surprising at all. We, in that case, would fail to reject the null hypothesis. We just keep on believing the same as we always have, or perhaps you could choose to do some further research. And so if I don't find enough evidence for the alternate, then I say, all right, well, I was trying to reject the null. That's the only reason you do a hypothesis test, is if you're trying to reject this status quo claim that you've always had. So I'm trying to prove it false, or I'm trying to show it false, and I failed to do that. So I failed to reject it. So we have to just keep on believing it. The alternate, the other option, is that you do find evidence to support the alternate claim because something was surprising in your outcome. In that case, you do reject the null hypothesis, and we change our minds to believe on what we believe is true. So notice that everything revolves around this null hypothesis, the one that is the status quo, that is assumed to be right throughout the whole process until the very end. So we either fail to reject it in the end, or we do reject it in the end. So here's some more key points. My notation, I messed up my notation here. This should be a subscript. My H naught does not, this is very important, does not require any evidence. This is like how innocence does not require evidence. This is assumed to be true. So you would never get to the end of a hypothesis and say something like, I found evidence of the null hypothesis being true. There is no such thing as finding evidence of the null hypothesis being true. We were assuming it was true anyway, so there is no evidence required there. The other point is that the H sub A does require evidence. This is like how there must be enough evidence to prove that someone is guilty. So in our write-ups, in our conclusions, if we are saying that we're going to reject that null hypothesis, that means that we did find evidence of the alternative. That's where the evidence is required. Below are some images of what the two-sided or two-tailed alternate hypothesis look like versus a one-sided or one-tailed hypothesis. So these images should look very familiar to you. Hypothesis testing is another spin on confidence intervals and on using the central limit theorem. So we could either have a two-sided hypothesis test where we're just claiming that the null is not true, and if we had enough evidence in either the above or below direction, we would be able to reject the null. If it's one-sided, if we're just testing that it has changed in a negative direction, then we would be looking for evidence out here in the negative tail. And if we were looking for a change in the positive direction, we would be looking for evidence out here in the positive tail. Okay, so after you identify the null and the alternate hypothesis and the type of test that should be performed, so you need to figure out, is this one or two-tailed? Then you need to choose a significance level, what it's called, a significance level that will allow you to conclude whether your data is different enough or surprising enough to reject that null claim. Okay, so the significance level, this may also look familiar to you, is denoted with an alpha. Okay, so we've seen this in our prior section. The probability, or what the significance level is it is the probability of making a mistake and rejecting the null hypothesis when in fact the null hypothesis is true. So this would be like concluding that a suspect is guilty when really he's innocent. So clearly that's a bad mistake to make, right? We don't want to do that. The significance level, alpha, is the probability of that happening. So we'd like to minimize that as much as possible, but again, we'll never be able to make it completely foolproof. We would never be able to get an alpha value of 0. The alpha value of 0.05, so 5% probability of making this kind of mistake, is pretty standard. That's the one you'll see the most often. Hence, did you notice, you remember what alpha is the complement of? Alpha is the complement of a confidence level, and what is the most common confidence level? 95%. So notice how those are related. Our most common confidence level is the complement of the most common significance level, and they are related that way, like that's a true relationship that you're seeing there. However, there are other pretty common confidence levels, so there are also other pretty common significance levels. Other ones that you're very likely to see are 0.005, 0.01, 0.025, and 0.1. Those are all pretty common as well. We will be told what significance level to use. If you are the researcher, you will be in charge of choosing your own significance level. And that is you saying, this is how much error I'm willing to sort of allow in what I'm saying. That leads us to a rejection region. This should be bold printed, so sorry about that. That is a definition. A rejection region is the region that is in the tail or tails of the normal curve that has an area equal to this alpha value. And here's the trick. If a test statistic falls in that rejection region, what that tells us is that there's strong evidence to reject the null. And so that's what we're looking for. Did our experiment bring us back a result that is so far away from what we expected? It's so far out in the tails, either to the right or left, that we say this is so surprising that I'm now going to change my mind, and I say that there's evidence to reject this null and go with the alternate instead. In the images on the prior page, the shaded regions are the rejection regions. And it says, notice that a one-tailed test, the shaded region is all in a single tail equal to alpha. So in the one-sided less than test, the shaded area over here to the left has an area of alpha. Or in the one-tailed positive side test, this upper tail has an area of alpha. But if we're doing a two-tailed test, notice that the entire rejection region has to have an area of alpha. When it's split between two tails, what that means is that each tail then has an area of alpha over 2. So that's what this next bullet point said. Sometimes you could hear this referred to also as the critical region or the alpha region. So all those things mean the same thing. Rejection region, critical region, alpha region are these shaded areas in the tails with area equal to alpha. Then the critical values are the number of standard deviations away from the mean that creates the boundary for these rejection regions. You can have 1 or 2 critical values depending on the type of test. So your critical values are these numbers down here on the x-axis, that boundary lines for your rejection region. These are your critical values.